All right, we are now in the organic chemistry section of the course. And organic chemistry is going to deal with organic compounds, which really means that they're going to be based on carbon and hydrogen. So organic compounds will be centered entirely around carbon. There are some other players that will be appearing in these formulas. So sometimes you will see oxygen, nitrogen, sulfur, phosphorus, or a halogen. And just as a reminder, our halogens are fluorine, chlorine, bromine, and iodine. So all of these formulas will be based on carbons and hydrogens with a few different elements scattered in there. So the first category of organic compounds that we will be taking a look at are hydrocarbons. And as the name suggests, hydrocarbons will be composed of, well, carbon and hydrogen. So these are compounds that are composed only of carbon and hydrogen in varying amounts. And this is a really broad umbrella term that encompasses lots of different types of compounds, and we're going to break these down further into more specific categories. The reason we're talking about organic chemistry is that organic compounds are all around us. So the vast majority of things that you encounter in your daily life are organic. Food is organic. One of the typical chemist jokes is that all food is organic because it's all based on carbon. Medications, so most drugs that you encounter are organic. Fuels, plastics, soaps and detergents. And last but not least, you are organic because your body is composed of organic compounds. So over 90% of compounds around us are organic, which is why organic chemistry is a really broad, large field, and there's a lot of work being done in it because it's so relevant to our daily lives. So as I mentioned, hydrocarbons, this is a really, really broad umbrella term that encompasses so many different types of compounds, and we really want to get more specific than that. So we're going to be taking a look at a way of classifying these things, and we're going to refer to what we call functional groups. So this is what we're going to use to categorize all of these chemicals. Because organic chemicals, there are hundreds of thousands of them out there, and we need to have some way of categorizing these things and classifying them. So functional groups, which I abbreviated as FGs because I get pretty lazy, so don't let that abbreviation confuse you. Functional groups are groups of atoms that have similar chemical and physical properties. So all of the organic compounds that we encounter are going to be categorized by their unique functional group. So we're going to learn a few of these. And the important thing is that functional groups are going to behave the same way regardless of what kind of compound they're in. So it could be a small molecule, it could be a really huge molecule with hundreds of atoms. It could be found in nature, or it could be made synthetically in a lab. It does not matter where it comes from or what size of molecule it's in. This group of atoms that we call a functional group is going to have the same properties, same type of reactivity, regardless of what molecule it's found in. There are going to be some formula conventions for writing the formulas of organic compounds. And what you're going to see is that we always write carbon first, then hydrogen, then other elements. So for example, if we were to write the formula of ethanol, it would be written as C2H6O. So notice how the carbon comes first, then the hydrogen, then the oxygen. So far we've been dealing with entirely inorganic compounds, and we're going to see that organic compounds have different types of properties. So there are some general properties of organic compounds. You will find that they have relatively low melting points and boiling points. And when I say relatively low, I really mean below 300 degrees Celsius. So they're not all necessarily super low, but they are low relative to inorganic compounds. So if you recall, inorganic compounds tend to have really, really, really high melting points, sometimes thousands of degrees Celsius. Whereas all of the organic ones will be, the vast majority of them are below 300 degrees Celsius. And this is really due to the fact that they have covalent bonding and their intermolecular forces are not ionic. So the attraction between those molecules is weaker than it is in ionic compounds. And you can kind of think about that intuitively, the fact that you can melt, let's say, coconut oil on your stove, but you're not going to melt table salt on your stove. Unless you had a really crazy specialized stove, I don't know why you would. They tend to be insoluble in water. They tend to be very flammable. So if you walk into an organic chemistry lab, you will not find a Bunsen burner. These things can be quite flammable. And they are generally less dense than water. So most of these are going to have some exceptions to them, but this is kind of a broad category of the properties of organic compounds. And if you think about the density of organic compounds, I would like you to think about whenever you've seen like articles about oil spills in oceans, that oil accumulates on the surface of the ocean because, well, it's not soluble in the water and it's less dense. So it sits on the surface of the ocean. All right. So now that we're talking about organic compounds, well, we're going to need to have some ways of representing that. We're going to be drawing a lot of these things. And I would like to remind you that every carbon has 4 valence electrons. And it wants to have 8 valence electrons to complete its octet. So that's our little reminder of the octet rule, which means if it has 4 valence electrons, let's doodle a little carbon here with its valence electrons. In order to have 8 valence electrons, it needs to make 4 bonds. And you will see that carbon in this class is going to be making 4 bonds, always and forever. No more, no less. In fact, don't ever draw carbon with more than 4 bonds. It makes me sad. It is very disturbing to organic chemists. This is where you're going to see that in hydrocarbons, well, hydrogen is going to come in with its 1 valence electron. They are going to share these valence electrons, and every time they share them, they make a bond. So when we do that, notice that now carbon has access to 8 valence electrons, completing its octet, each hydrogen has access to 2 valence electrons, and hydrogen is happy with that, right? Hydrogen is one of those exceptions to the rule. It only wants 2 valence electrons, and it is good. And this is the structure of methane, or CH4. So this is a Lewis structure. This is how we have been drawing our compounds thus far. You're going to see some other different types of representations of organic molecules, some of which are listed here. So if you look at this first one, the space filling model, this black atom in the middle is representing the carbon, and these gray atoms are representing the hydrogens. So notice there's 1 carbon in the middle, 4 hydrogens around it. And in the space filling model, it really kind of expands all of these atoms out until they look like these big doodles. The ball and stick model is showing us the tetrahedral geometry. So notice that in this Lewis structure, it looks like a flat planar molecule, but we know that that's not the case, right? CH4 is going to have tetrahedral geometry where this bond is coming out toward us, and this bond is going into the page away from us. So the ball and stick model is showing how these atoms connect and the geometry in which they are oriented. Now, of course, I like these doodles. I think they're helpful. They kind of represent molecular models that you will be playing with. And you can see how everything connects, which is nice. But drawing these when you have really large molecules would get very, very tedious. So organic compounds can get really large. You can have things with 50 atoms or more, and having to draw this for every single atom would just be insane, right? Nobody has time for that. So we do need some more convenient ways of representing these things. CH4, the condensed structural formula, this is just like all of the other molecular formulas that we've been writing, where it's listing each element that's present and the amount of each element. So the little subscript here is telling us that there are 4 hydrogens for every 1 carbon, and it's representing our Lewis structure, but it's not showing how those bonds actually connect. So this has been fine so far because we haven't needed to see how things actually connect. But you're going to see when you get into the organic section that a molecular formula, sometimes you can have 26 different compounds that behave differently that all have the same molecular formula. So this is not going to be informative enough. We're going to need to be able to show how those bonds connect. The expanded structural formula shows us how those bonds connect. And this is basically the Lewis structures that we've been drawing. This is just like your standard Lewis structure, where those bonds are drawn in and show you how the atoms connect. However, this is not telling us what this molecule actually looks like in real life because it looks flat and planar. So the wedge and dash model is really representing what this ball and stick model does, but in a more convenient way that's easier to doodle. So in the center, we see our carbon. This wedge is showing us that this bond is coming out toward us out of the page. And this hash is showing us that this bond is going into the page or behind us. So behind us, and this one is out toward us. So you will see a lot of the wedge and dash model being shown. And next we're going to talk about how to convert between the condensed, expanded, and wedge dash model formulas or line angle formulas, which we'll talk about next.